Hello, everybody, and thank you for attending today's webinar titled Understanding and Troubleshooting the EDAX Indexing Routine and the Hough Parameters. Before we begin, I'd like to cover a couple of basic housekeeping items. At the bottom of the console, there are several kind of buttons you can use. If you have any questions during the webcast, you can click on the Q&A, submit the question, and I will go ahead and see it. I'll try to answer some of these questions during the webcast, but if a fuller answer is needed or I run out of time, I will, of course, answer these by email. We do save all these questions, and again, I'll get to them. A copy of the slide deck is currently available in what's called the resource list. It looks like a green folder. You can also expand the slide area by clicking on the Maximize button or by dragging and clicking and making it bigger. If you have any technical difficulties, please click on the Help widget itself. It's like a little question mark and covers common technical issues that you may run into, either audio or video-wise. And of course, when we're all done, the webinar will be on demand, and that'll be live approximately one day after we go ahead and finish this. And with that in mind, and kind of wrapping up the housekeeping, I will of course tell you who I am. I, of course, am Sean Wallace. I've been with EDAX now for close to 5 years as an application engineer specializing in EBSD. I also do cover EDS and WDS as well. My background is, of course, geological, and I've used EBSD electron microprobes, all kinds of mass spec, and even some computed tomography in my previous careers in research. And of course, from those levels, I taught, from postdocs to undergrads to little old ladies off the street, and some space science kind of things. So I earned my master's degree in geology from the University of South Carolina, mainly using ICP-MS to understand what's called geothermal barometry. And then, of course, went from there to work at the American Museum of Natural History to understand the origin of the solar system using EBSD and other techniques. Of course, when I'm not doing that, I like to play with rocks because that's kind of what I do. So, with that in mind, again, our topic today is going to be understanding and troubleshooting the EDAX indexing routine and the Hough parameters. The reason I chose this topic is I think it's really important to understand what's going on behind the scenes to fully understand your data, the quality of your data, and of course, in the end, to get better data for yourself. So the basics of the EDAX routine is this general basic workflow, right? First step is you collect the patterns. The second step is you use this magical Hough Transform to find the lines. And then, of course, those lines that are used found in part 2 are then used from the indexing routine to actually get the orientation from that. And again, from step 1, 2 to 3 there, some people it's a little bit more of a black box than they would like. Now, again, step 2 is really one of the most important parts of EBSD, is this Hough Transform. And while I think it's not all that important to understand how the Hough Transform is built upon, and honestly, there's YouTube videos out there that cover that way more than I'm going to cover in this little webinar. It's by far the most important, but you have to understand how the parameters that we deal with to use the Hough are more important than actually how the Hough is made. Now, of course, starting with good data is very important there in step 1, and this webinar is going to cover more of step 2 and step 3 than step 1. Now, if you can't get a good pattern, there's always webinars on that, and there are 2 webinars out there that work to kind of show you that, and these are the resources for these webinars. So here we can see I have a webinar on understanding and optimizing EBSD camera settings. That covered the older Hikari series. I will tell you there are some differences with the newer Velocity because of the camera architecture being different between the CMOS and the CCD, but honestly it makes it easier to do that. And then, of course, there is, besides optimizing pattern for collection, you can also use OM analysis to optimize it after collection using things like NPAR and other image processing techniques. And of course, I have a webinar on that. So, again, those are on demand, and you can go ahead and watch them for free whenever you want to. Now, again, with that in mind, I see quite a few new faces on the attendees list, which is always great. I always want to kind of, help me get the word out there of this kind of interesting novel technique of getting our information. And with that in mind, again, I have a little poll for you guys to say, how many webinars have you guys previously watched? and just kind of give us an idea of who I have here that's new, because I know some of you guys again definitely are new on this list. I mean, there's plenty of people on here that definitely know me, and I definitely know you, but especially the overseas group here, I don't know a lot of you. So let's see here. Let's see how the results have gone. Actually, pretty surprising to me is that about 40% of you guys have never actually watched a EDAX webinar. That's good. I'm happy that you've been here, and hopefully, in a couple months, you're down on the more than 3, and we're always happy to have you and spreading our knowledge of what our products can do. So now let's go ahead and dive into the fun stuff. What is the Hough Transform? How is it kind of built? And then again, how do we use that to actually find the lines? So the Hough Transform is this fancy image processing technique of finding features inside of images. We use it to find lines. There are other ways to do things like circles or edge detection or whatever you want to call it. And again, those aren't really what we need to do here. And the Hough Transform is kind of been kind of this weird feature where we started using it when we originally started doing EBSD in kind of in the mid-90s, doing EBSD live and automated, and it's just kind of worked. And we optimized it for our work over the years and does a really good job. Now, what it really does is it turns your EBSD pattern into what's called row theta space. And this row theta characterization, essentially, you walk through each row in theta, you find a pixel coordinate, transform it, take the grayscale values, and as you step through this, you take each basically point on a line, go ahead and find another point on the line, and you get these row theta parameters that go through that point, and eventually you get these sinusoidal curves, and these sinusoidal curves are basically that line. And what happens is you keep doing this over and over again, they will converge over and over, and you'll get these hot spots that are actually lines. So here we can see, again, we have all these sinusoidal curves. They kind of meet in certain areas, and there we go, and we actually get the point on that. So again, a line is transformed into a point in Hough space. Again, I'll tell you guys, it is not that it will be, it's not really key to understand that, the full basics of the Hough Transform. Again, just realize that it takes a point into a line. And again, one of the key things to remember here is that we have to do further image processing to actually find the feature here in the Hough Transform. So here you can see that it's kind of bland in the background, but this dark, light, dark pattern is kind of key. And we'll talk about this dark, light, dark pattern and how it's kind of formed in a little bit more. So in the end, when you get the actual Hough Transform, this is what you have. So on the left, you have the pattern, and here you can see, of course, in colors, the colors kind of match up to where the Hough point is on the actual EBSD pattern. So they're going up and down. Straight in the middle is the yellow guy, and you can see down the more kind of in the middle there is the red guy, which is kind of on the bottom. So again, you have row from 0 to 180, and you have the theta. Excuse me, I said that backwards. You have the row fraction from basically inside to out, and then you have the theta from 0 to 180 degrees. And again, this is just how we kind of find the lines. And again, the key thing with this is the computer actually has to be able to find these features in the Hough Transform, and these are going to be controlled by the Hough parameters. So where are these Hough parameters kept? And again, we'll talk about these kind of in details. This is one of the things I probably should have blown up in the end. You can see here, this is going to be Apex, so you guys mostly don't have Apex because it's not fully out there yet. But here you can see we have a Hough tab, and over on the left-hand side, I have all of my Hough parameters. These Hough parameters are going to be things like theta step and min-max distances. These are the lesser used ones. I'm going to talk about things like vertical bias, max bands, and the effects that these have on your data because, again, most of these Hough Transform guys aren't used all that much. But the ones you use can have big differences on your data. The ones that are kind of niche, I'm not going to cover in detail here because, I'll add probably another extra hour to the webinar, and you guys wouldn't actually use them that much. I'll give you kind of corner cases of when they would pop up, but I wouldn't go any deeper than that. So we found the lines. Now what? So with the Hough, I've already done it, and again, I'll cover the Hough in more detail later on. Our next step of this is going to be building what's called the lookup table from a phase list, and from that phase list, we actually choose both our phase and our orientation. Now, I will tell you that one of the most common errors that pops up with this is going to be overpopulating this phase list. So there's a couple downsides of this phase list, and when you populate it, you're building this lookup table, and it has to basically compare each pattern and the lines found from that pattern to everything in the lookup table. So if you have 10 phases loaded, it's comparing it to all 10 phases. So again, always kind of keep that in mind. Don't overpopulate the list. You want to do your phase ID and figure out what's in your sample before actually running a map. And again, if you just brute force it, all you're really doing is slowing everything down and also causing more errors in your data that you have to clean up later on. So again, don't overpopulate this phase list, and that's going to be one of the most common problems. And I'll actually show you an example of that later on. This phase list is it could be in the phase tab. You can go ahead and click on phase, and you can go ahead and search for whatever you're looking for. So here we can see our little search kind of engine inside of Apex, and you can see again things like searching by chemistry, space group, whatever we have in there. So there's plenty of options to search by. In the end, you basically click on them and then move them over. And again, the phase list of one you're going to be using is going to be on this right-hand side. So here we can see I just have a nice generic phase listed over here, and that kind of does the job for what I was working on then. Now, the structure tab, when you actually click on those phases, is again what the lookup table is going to start building off of to look at what we call the interplanar angles. These interplanar angles are going to be essentially the lattice planes themselves, the diffracting planes, and how these kind of orient themselves versus the camera is how we get the actual orientation off of this. Here we can see we have our lattice parameters, we have our atomic positions, and of course the reflectors based off of that. And again, this data is usually already done for you via either our internal phase list and database that we've made over the years of doing this, and then also from, of course, outside vendors like ICDD, the ICSD, and of course the AMCS. So again, all these data sets are available to you. You can go ahead and search them inside of our little search engine, and I'll go ahead and pop them up. Now, I will tell you that, again, this is one of those dangerous things here is that, one of the flaws not the flaws of EBSD, but the downsides of EBSD is, again, you're looking at these structure files. So the structure file is the same between two phases. It can be a problem. And again, we'll talk about that in a little bit more depth later on. So how do I actually build that lookup table? Well, what I do is I identify the high contrast bands because these are the bands that the Hough Transform is going to see. So some of this is going to be a structure factor characterization, and that's a big giant mathematical equation. I'm not going to cover that here. But essentially we say, okay, in this guy here, I see the 200, the 111, 220, and the 311. And then we basically start expanding that and say, okay, from there, what are the symmetrical ones I can expect? And then from that, I find all the pairs. And then I go ahead and calculate all the angles between these pairs that I expect to see. Cool. Now I have this big giant list of all these planes and all these angles. And then luckily for us, this is one of those times in the EBSD world where symmetry is our friend, and we go ahead and basically throw in all the duplicates and sort them. So again, I've taken this one single phase file, found which lines I expect to see in the EBSD pattern, and look what angles I expect to be between these actually visible bands, and then again kind of throw all the duplicates out. Again, a thing to make clear here is that if I'm loading that phase file, I'm not just doing this for that single phase, I'm doing it for every single phase I'm looking at. So when I start talking about the voting algorithm later on, I now have an ever-expanding kind of block of information to look at here because this interplanar lookup table can start getting bigger and bigger and bigger. So again, this is why I always tell people to not basically overpopulate this list because you're going to start to see some performance issues when you do this. And again, for lower symmetry materials, you have basically usually more reflectors and more reflectors at weird angles, less symmetry. I can't throw out as many as step 5. And because of that, in the end, again, this table is bigger for those kind of things. So what we basically do with that is we match these. I say, okay, I have an angle of 31 degrees. This is going to be, the 220 or the 311. Or maybe I have 35.1 degrees, and that's 311, and also the 311. But that's kind of a dangerous way to think about it. And the other thing here is to realize that these angles here, really have to, you can't measure these with your eye. And the reason you can't measure with these with your eye is really because you're looking at a projection, right? So you're looking at a projection on a phosphor screen that's usually angled not quite, 90 degrees to that. So these are going to, of course, be distorted. So don't take an EBSD pattern, try to measure it by your hand and say, oh, this should be this angle. You really have to consider, the entire kind of path length of what's going on there, how things are tilted, et cetera. And that's all taken care of by the software and the initial calibration. So again, most of your systems aren't at a full 90 degrees. Most of your systems are slightly tilted to help with space issues or solid angle issues or things like that. And that's where we're very happy to have our mechanical engineering group do their hard work of basically optimizing those port covers and drawings to do that. So again, these angles aren't going to be exactly what you're measuring. They're going to be based on the projection. Now, what we do with all this is essentially, again, I say, okay, I have what we call these triplet solutions, or I'm looking at the angles between different things, and we can go ahead and say, okay, here again I have these angles, and we're good, right? So here's my red guy, here's where my blue guy could be, and this is the other guy. Now, why have I basically opened up this angle that I know this angle is? Why have I opened up the actual space to go ahead and basically make it more than one choice? And that's because, again, there's errors kind of being propagated through all of this. So we have in the software what is called the interplanar angular tolerance value. And that is, again, used to say, okay, I know this guy is measured 55 degrees. For the voting algorithm, let's go ahead and open that up to say, okay, maybe it's going to be plus or minus 3 degrees. And the reason I just said 3 degrees is because by default, that 3 degrees is what we use. I will tell you there's almost no reason to change that value in the software. In fact, I'm probably not even going to tell you where it is. That's kind of one of those kind of things. If you change that value to be too big, again, you're changing that lookup table in the voting algorithm just to make it do so much more work that you're not gaining anything for it. And if you go the other way, you open up yourself to errors that you might be missing correct orientations because your lookup table is basically looking at a too small of a change in the angles versus what is actually measured. So again, we basically go ahead and do this, and then we go ahead and go from there and say, okay, here is what it is. And this is going to be based off of the voting algorithm. Now, what I will tell you here, and this is slightly wrong in this slide of how we do things, is this is a triangle. It doesn't have to be a triangle. Just visualize it as easier as a triangle. So we don't really use pure triangles. I don't have to have, this blue guy being over here to make this triangle. This could be on the left-hand upper quadrant, and that could be what I would be using for the triplet. Again, it doesn't have to be a triangle per se. So here is my solution. How did I actually get this solution? Well, we'll go ahead and step back a little bit. The amount of solutions I'm going to have, amount of potential triangles I have, is going to be based off of, I have my brain a little bit backwards right now. So when I vote for this, essentially what I'm doing is seeing how these indexing solution works for each one of these triplets that give me the orientation. So now you can see I have, a possibility of 10 different orientations here, or 10 different indexing solutions. And then here I can see option 3. Each one of these triplets works within this tolerance angle, and it's kind of like basically kind of bound together in this. So let me go ahead and just kind of re-explain that. So again, each one of these solutions here, I have a possible orientation. And this guy here, like number 3, I can see that each one of these triplets is within the tolerance angle. So each one of these guys gets a check mark. So this orientation basically is saying, hey, this guy has 10 votes. And that guy next to me, number 2, has 4 votes. Number 3 here has got the most votes. And that's going to be, again, the kind of guy who wins it. We'll be saying that, just to make sure here, my amount of questions I have is actually less than I thought. So I just want to make sure everything is working. So if you have a question, again, feel free to use it and ask. Now that I have these votes, again, the amount of votes is going to be based on the amount of lines I have. And the amount of lines I have, let me just go ahead and kind of zoom this out real quick. You can see again that essentially most of my votes are going to be kind of clustered together, and that's kind of what I want. Let me take the orientation average of these 10 solutions, and that's what your actual orientation is going to be. Now, how many lines I actually have is going to control how many triplets I have. And here you can see kind of the math for this. This is, again, one of those values that some customers like almost never change, but it's one you really should be changing depending on what you're doing. And that can be kind of depend on your symmetry or your samples. So here you can see that if I change the amount of bands I use, which is going to be one of the main parameters in the Hough, I get more and more possible solutions. That means I'm going to have more and more possible votes. So in general, for most higher symmetry materials, 7 bands works. So if you're just dealing with FCC and BCC as kind of your everyday thing, the default is going to work fine. And that works pretty well. Now, if you start to go for lower symmetry materials, it's often useful to use more lines. And I'll say this is one of those things that me and my colleagues kind of discuss all the time is again, how many do I use versus how many do they use? And what I usually use for most things, if I'm using a hex-based material, I will often use like 10 lines. And if I'm using geologicals or ceramics or something, I will often go up to 12 lines. So I'm getting many, many more votes. I'm using more lines. But of course, I am going to be paying a time penalty for this because, again, I have more lines, I have more triplets, I have more votes, I often have more phases. So suddenly now I'm just kind of blown up this whole kind of computational time needed. So it's just big time penalty. So don't use 20. There's really no reason to ever go over 12. If you start going over 12, what you'll see is that you will have essentially you'll start getting bad Hough lines. And while the indexing routine can take care of that, you start getting too many, you will start getting bad orientations. And again, I'll actually talk about that later on, how with some certain patterns or maybe some certain setups, you'll have issues where you actually want to work around these bad Hough lines using some of the Hough parameters. So now I got my votes. You can see how many votes I would possibly have. Understanding the quality of your data is going to be this concept of what we call, competitive index. And this is one of those things that is good to understand, but also a good thing to understand how it works because it can kind of either give you the wrong idea that your data is good or the wrong idea that your data is bad. So again, it's very important to kind of understand what's going on. So what's going on? If we look back at my initial kind of question here, I had that guy, that one pattern, and I had solution 3 was my winner, and it had 10 votes, and solution 2 was my second best. So the CI value is going to be the difference between those over the amount of total votes. So here I can say that, again, solution 1, solution 3 had 10 votes, solution 2 had 4 votes, and I had a total of 10 votes. So in this case, 10 minus 4 is 6. 6 divided by 10 is 0.6. This right here is a CI value of 0.6. What does this value mean? Well, I always tell people this is a measure of uniqueness between, again, the first solution and the second best solution. So we can already kind of see where this would go down is if I have 2 very similar phases, in general, I'm going to have a very low CI. Or if maybe I'm really lucky and have, a perfect orientation and it's got 10 votes versus 0 votes, and I'm going to get, a very high CI. If that phase list is too populated, something is just going to have more votes just kind of by random chance. Because of that, that's also going to kind of lower these CI values. But in general, what is a good CI value? Again, this is usually we're looking for this CI value of around 0.1. So in this case here, that'd only be a 1 vote difference. How big a difference is that 1 vote difference? Well, it's actually pretty strong. And this is done from our numerical simulations that Stu does. And what you can see here is that a confidence index of 0.1, your orientation correct percent is going to be over 90%. And then by the time you're around 0.2, you're essentially asymptotic around 100%. Again, how big of a difference is that? That's 2 vote difference in something that has 10 votes. So 10 versus 8 is a pretty kind of a strong CI. So if you're doing something like simple like an FCC material and you're getting CIs of 0.8, 0.9, you should feel really, really comfortable with that. If I'm starting to get something around 0.05, then maybe I want to start thinking about hey, is this correct, or what can I do to get it better? And if I have a CI of 0, but my data looks good, then I really need to understand what's going on. Again, I'll cover that a little bit more later on. So if you guys ever heard of this before, this confidence index stuff, again, it's really kind of important. And if you look at our cleanup webinars, talking about OIM analysis, we use this CI as a filter of good data versus bad data. And again, I will tell you, there's kind of this, I always kind of argue with my colleagues, some of them choose more of a 0.2 value because, hey, here I feel really comfortable because it's more asymptotic. Here, I also have the 0.1 value is kind of what I use because I usually feel pretty comfortable. And I'm going to check those values to see in my OIM analysis how well I feel that it is mixing correctly. Now, my map is speckly or something, it's still 0.1. I would still probably try to clean it up a little bit more to understand why it's 0.1. Say, hey, how well do I actually believe that data? So again, how well can I kind of trust that CI value? This right here is our good old friend, our high gain nickel data set. So if you have OIM analysis, you have access to this data set. And what I did here is essentially overpopulated my phase list on purpose. So in this case here, I use nickel and generic FCC. They're not quite the same, but they are relatively close. And here you can see on the left, I have my IPF map. And if I'm looking at my IPF map and I look at this, I can say, hey, this looks pretty good. I have nice consistent grain boundaries, no speckling really on the grain boundaries. I have twin features. I have some minor deformation. This is a good IPF map. Now on the right, I have my CI map and my legend down here in the corner, and I can see I have this nice little blue, and I can see there's like 3 pixels that are not blue. Essentially what this is telling me is that my CIs are low all over the place. So what I just told you here is, hey, if the CI is relatively low, I need to think about, is this data good for what I need it to be? And the easiest way to look at that is say, okay, again, why is this CI low? I already kind of told you why. It's because I overpopulated this phase list, but again, I can see that if I actually look at this phase list, right? So you can see this phase list, again, nickel and FCC, and it's basically 50-50. It's pure noise. The indexing routine really can't figure out what phase it is directly. So instead of giving an actual phase and saying, oh, hey, this is 100% nickel, it's basically flipping a coin and saying, oh, this pixel is nickel, this is FCC. Now, the question here is this data good? Well, my phase map is bad, so my orientation is correct. So, I really have to think about what am I doing and what's my purpose of this data. If all I care about is the orientation data and general textures, this data set is fine. Now, if I was trying to say, okay, what are my phase percentages and does each phase have a texture? Well, I can't actually do that because, again, this phase map is pure noise, and if I actually used this to kind of partition by phase, I'm not going to have any data that makes sense. So again, it's important to kind of understand, what the CI map is actually telling me versus my orientation and what I want to do with that data in the end. So let's go ahead and actually start kind of talking about the Hough parameters themselves and not just kind of metrics beforehand. So here we can see the Hough problems, and this is off OIM analysis 8. I will tell you guys that honestly, I do very little work on the microscope anymore. And this is, I don't know if it's personal or what, but I don't tend to do the same thing over and over again. So essentially, if my patterns look good and I believe they're indexable, I'll just let the kind of computer do its thing. I'll make sure it's set up, got the right phases, and if the data isn't perfect, I'll go ahead and rerun it inside of OIM analysis. So these right here is the Hough page inside of OIM analysis. So again, go ahead and look at my NPAR webinar, and it talks about how to get here. But in general, you find a little beach ball, click on the little beach ball that's the color Kikuchi pattern, click on the actual map, and it'll go ahead and open up the patterns. In the end, it'll open this up. Again, if you're doing this, you need to save patterns. So make sure you have saved patterns if you're working on this. And the different Hough parameters I have is going to be things like pattern size, theta steps, row fractions, max band count, convolution mask, minimum peak magnitude and distance, symmetry, and then vertical bias. Now, what I will tell you here is that some of these are very rarely used, and some are also more commonly changed. The more commonly changed ones are going to be things like vertical bias, row fraction, and max band count. And those I'm going to talk about a little bit more in detail, so I'll go ahead and I'll talk about those later. But let's go ahead and kind of talk a little bit about the less covered ones. And these I'm not going to have slides on these later on, because again, they're not used often enough to really spend that much time on. Things like the pattern size and the binning is just something, honestly, I don't change. Back in the day when computational time was more important, the Hough was kind of your limiting factor. So you would bin the Hough down to match your patterns, and from that you would save computational time. I just don't run into that as my choke point anymore. The other one is going to be the theta step, and then this is going to be when it's actually making the Hough. When it does this, is again, how often am I using this theta step to actually build the Hough, and you can be from 0.25 up to 3 degrees. The default on this one is 1, and again, this is a value you very rarely need to change. In general, it will give you slightly better precision if you do change it on the Hough peaks, but not anything worth writing home about. So if you're trying to get like a super precise orientation off of something that you really, really need, yes, you would change this data step to be smaller, down to 0.5 or to 0.25. Again, realize that the computational time to build that is going to take longer. Data step 2 or 3 is going to be done if you're really trying to push speed. So again, if I'm really trying to push that full 4,500 degrees, I'm going to change that data step size to 2. And again, I need that for computational reasons. Trying to do the Hough, 4,500 times per second is very difficult when I'm doing a relatively fine Hough-based data kind of calculations. Beyond that, we have the convolution mask. I'll talk a little bit about that. Essentially, the convolution mask is a way to increase the contrast around the Hough peaks, which makes them easier to find. And that is going to be key for some kind of niche cases. We either have a high Z or not really a high Z, low Z material. But if I have either a very large lattice or very small lattice, the band space can get changed, and because of that, I have to tell a different kind of area to look at. The minimum peak magnitude and minimum peak distance are again kind of niche cases of when they actually need to be used. And usually when you have to use that is when I'm getting for some reason I'm getting a giant cluster of all of my Hough peaks in one area. So down here, this is kind of the pattern down here on the top right or bottom right. This is the Hough Transform. Let's say I had everything down here in the bottom right-hand corner. Now, that's not really giving me an orientation for the whole pattern. It's saying, okay, I'm taking a subpart of this pattern, and that's not really what I want. I want to have kind of full coverage over the full Hough area. So what I do for that is I can change these minimum peak distances and kind of spread it out. Or I can change this minimum peak magnitude to make sure, again, I'm getting stronger peaks. And again, I very rarely use that. I say one of the most common times I have to use that is with things like orthorhombic materials, where I will often get this crazy amount of bands around a zone axis. And because of that, it can cluster around that zone axis, and that's what I'm trying to avoid by increasing this minimum peak distance. Again, it kind of spreads them out. And the symmetry one is often, again, it can be used if you have an unsymmetrical peak, but again, very rarely do I change that. So with that in mind, let's go ahead and kind of discuss a data set that I got from some customers, from a user. So for most of this kind of troubleshooting of the Hough, I'm going to be using a relatively difficult sample for a couple of reasons, and that's going to be ice. So, just think about ice, it is it can be crystalline. It is a relatively lower symmetry than, plain FCC. You have relatively poor pattern quality due to low Z. It has tight bands because of the small unit cell. And of course, you can have artifacts in the patterns themselves because of the very nature of what you're doing. You can have shadowing due to the setup in the microscope for the cold stage. You can have, just surface roughness in general because of what you're doing. And of course, here, again, it's data as courtesy of some people, mainly at the University of Pennsylvania, and I thank them for the chance to take this data and again kind of show you what we can do with it. Now, if you've actually, you might have actually seen some of this data before in our recent Insight article. I use this data for that. And that data is more focused on increasing the pattern quality and the background issues caused by the setup, not for actually troubleshooting the Hough and the indexing. So again, same data set, but from a kind of a different perspective. So the data set as received looked like this. And you can see again that I can see some coherent grains, a lot of kind of speckling in areas, and as I look at the pattern on the bottom left, there's just not much on the bottom left. There's just not much there. So it's showing kind of inconsistent indexing and missing data over large areas, and again, this IPF map is kind of telling me that I got more work to do to pull the data out of here. Again, some of this is pattern quality, it's pattern as collected. So again, I need to go ahead and do a better job. But again, I don't do a better job just by collecting it. I can use things like NPAR to kind of pull that out. And this right here is the IQ map, and here again, I can see nothing really good here on the IQ map. And the IQ map is basically saying, hey, I'm not having much information in my patterns, and because of that, I'm having trouble indexing it. Again, while the patterns are low quality, things like NPAR can really kind of fix up this data, but even then, it still needs help with the Hough. So, and this is the CI map as collected, and again, you can see even where the areas there's indexing, it tends to be relatively blue, which means relatively poor quality. So again, I need to think about this, I need to question the data and try to do kind of a better job of getting it out. So the first thing is really understanding is I want to go ahead and actually start tweaking this vertical bias. And the reason I want to tweak this vertical bias is if I look at a lot of the patterns in here, I can start to see artifacts and kind of clustering down low. So this is, again, an OM analysis. I can see that if I'm going to have artifacts or issues, it tends to be near the bottom of the phosphorus screen. Again, it can be damage, it can be shadowing due to maybe fib curtaining or general roughness of the sample. But again, most of my artifacts are going to be towards the bottom of my screen. Now, what we can see here is I also have like this guy right here on the bottom. I probably should have circled it. This is a bad Hough line. I also kind of have this weird kind of black smudge over here on the right side of the pattern. And what I want to do is I want to bias the Hough away from choosing those as lines. So what I do here is I can go ahead and take this vertical bias value, increase it a little bit, and it'll basically say, hey, bias my Hough lines towards higher level lines, so away from the bottom. And I go ahead and do that. And I usually change this vertical bias by default for almost all my work level around 3%. And again, it just helps me give a better coverage over the whole area. And if I go ahead and do this, what we can see here, again, in this case here, I've actually increased this guy to around 7 or 8% to get away from these guys in the bottom right-hand portion of the Hough transform. And now you can see I'm getting a little bit better coverage because I'm getting lines up in the top left, and of course around like 11 o'clock, another one around 11:30 or so. So I'm getting better coverage over the full area. I'm not getting these worse lines over in the top right. And again, if I could go ahead and look at these side by side, you can see that again, I just have better coverage of the full area, and I'm not getting bad ones. That's really kind of what I'm trying to do here is get away from this. So I got a question here asking if the change in vertical bias, is there a change that will shift the PC too high? No. The PC in this case is going to be the pattern center. This is going to be disconnected from the actual calibration itself. So the calibration says your pattern center is at this position on the phosphorus screen. When I choose the vertical bias, I'm not actually changing anything to do with the calibration per se. All I'm doing is basically saying, here's my Hough transform. When I find the lines, don't use the bottom part, kind of bias myself towards the top. That's all. Again, I'm not actually touching the calibration of the PC center shift at all. Here we can see that, again, I've essentially biased myself up. I've spread myself over. And if I go ahead and click on reindex and go ahead and run this through, I get something like this. Again, I'll also tell you, again, this is done with NPAR. So NPAR is kind of increasing my pattern quality, but even with a better increase in patterns, again, this is, let me just kind of jump back to a couple slides. This right here is my pattern quality now. So my pattern quality with things like NPAR and some other data corrections, I have patterns like this, where as the data as received, my patterns look like this. And again, there's real no pattern there for me to index. So again, I'm thankful that, in this case, image processing techniques existed that allowed me to get a pattern like this. But even with those, I get an indexed results that while I'm getting pretty good coverage, I can see that in certain ones of these grains, I'm speckled. So here I can see in the areas I have marked in red, you can see that inside of grains, I'm bouncing between two solutions. So in the bottom right, I have purple and green. It's consistent, but it's bouncing between two solutions. If I look at the top left there's 3 grains that are kind of clustered by that, again, are bouncing between a couple different solutions. Now, this could be a pseudosymmetry problem. In this case, it's not that. It's that I don't have enough good bands to give me a unique solution. So if 2 solutions are being basically bounced between. And I'll see that when I actually do this work and you look at the CI map, you'll see that the CIs are essentially are artificially low because, again, it's bouncing between these 2 solutions. Now, in general, again, this is going to be a common problem if I don't have enough lines. I also will see the speckling, again, if I'm doing a hex-based material and I keep it relatively low amount of lines. And you'll again see that later on too. Now, the other thing I can change is going to be the row fraction. And again, what the row fraction does is when I'm doing this Hough transform, here you can see the Hough transform. You see these black areas? This is basically the edge of my phosphor screen. So again, I've turned that round circle into kind of this rectangular by doing this Hough transform. Again, this is using basically the full area of the phosphor screen. What I can do is I can essentially bring that row fraction in, and that brings in basically the inside or the outside of the phosphor screen inside to basically mask off the outside. Now, what happens here is that I can get around artifacts near the edges of my phosphor screen. And again, it's going to be really useful if I have again, either something shadowing me or whatever. And what can happen with that is it'll give me this kind of this dark edge. And what happens with that is that the actual Hough will use this dark edge to say, hey, I have a feature here, and I'm going to go ahead and use this feature as part of my indexing. So on the right-hand side here, you can see I have 3 Hough lines that are being defined because of this feature. And I went ahead and bring that row fraction in. To go ahead and hopefully get away from this feature from actually using the Hough line. Now, what I will tell you is that our indexing routine will actually see that these triangles don't work using these lines, so it won't get votes. So you won't get a bad orientation from this because it won't find an orientation based off of this, so to speak. But it will lower your CIs artificially. And again, so in this case here, I would use this row fraction to go ahead and bring this in. When I do this, what happens as you can see, I've now masked off on this right over here. You can see I started to mask off the top and the bottom. And again, remember, this is a row fraction, so instead of being a circle, the Hough transform is turning this into a rectangle. So I'm basically bringing in the circle, which means I'm cutting off the top and the bottom of the Hough transform. And when I do that, you can see over here on the left-hand side, there's this kind of this swooping artifact over here based off of the area that we saw. And I can see that I have some very inconsistent Hough lines that are being picked up over here. So I'm actually having 4 incorrect Hough lines being identified out of, I think, or out of 10. So 40% of my Hough lines are wrong. So when I can deal with 4 bad Hough lines, I don't want 4 bad Hough lines. So if I bring that in a little bit, in this case from 90% to 75%, I've now maxed those off. And I can see that in these blue guys up here, I have 2 Hough lines that I probably feel more better about being correct. Now, there is a danger of overdoing this row fraction. So if I start getting less than a certain percentage here, and I probably wouldn't lower it less than like probably 65 to 70. If I bring it in too far, what happens is I lower the solid angle of the system, and then I'll start running into indexing problems because I'm not looking at enough information. So again, don't go crazy on this and say, oh, I'll just use 3%, because then I'm looking at too little information to actually get a good quality orientation off of that. But again, now I've lowered this guy just by going from 90% to 75, I've gotten rid of this artifact. And again, this kind of swoosh artifact is really, really common with things like shadowing or backgrounds, or depending on what's going on, especially with a lot of fib work. I tend to get, background issues or curtaining issues that cause artifacts in this lower part of my phosphor screen. So by combining both the row fraction and the vertical bias, I get away from these problems. And again, this solves so many problems that I run into. Now, the real next question here is how many bands to use? So again, here I've been using 10 bands. So how many bands do I use? Well, it's really depend on the phases or the phases present, and you actually can model this in our simulation tools. And here you actually use team. This isn't brought over to Apex yet, but will be hopefully in the near future. And you go to Simulation tab and you click on Confidence Index. You actually can model this and say, hey, I'm using 7 bands for a hex material. How many bands, in the orientation space, how am I looking? And again, you can actually do this for any different phases. So here is an alpha beta titanium. Here we can see that if I use 4 bands, so this is basically your pole figure. This is my phase space, the way to think about this, orientation space. You can see that all these blue areas basically say, hey, if I'm using 4 bands on an alpha beta sample, alpha beta titanium, I can't get a unique orientation based off of the not enough bands in these areas. As I go to 5 bands, these area lessens. As I go to 6 bands, again, I'm having issues with some orientations. So I can kind of say, okay, how many of these bands do I want to do? And say, okay, again, what do I want? So again, if I'm using something like alpha beta titanium, I will often use 8 to 10 bands to make sure that I'm getting good phase separation on number of bands. Because again, the key thing here is this is 10 correct bands. So if I have some wrong bands, this is going to be lower this and basically shift it to the lower guys here. Here again, you can kind of see the actual effects of this data from one of my colleagues here at EDAX. You can see that there's some speckling and some issues around. I go from 4 to 5 to 6 bands. You can see that this big green grain starts getting less and less speckled. And then, of course, those effects kind of go away a little bit as I get to 8, 9, and 10 bands. Now, if I actually look at this as a phase map, you can see how much wrong misindexing I was getting in this example here with the dual 5 titanium with the 4 bands. Basically, most of the green in this guy was incorrect. And because of that, he wasn't using enough bands. As you increase your bands, you can see your phase percentages changes from, in this case, around 85-15 to closer to 100%. So he was getting quite a bit of misindexing here, just based off of that. And then if we kind of again look at this, getting rid of the bad data points, again you can see if I use a CI greater than 0.1. You can see it gets better and better and better based off the amount of bands I have. How about for ice? So in this case here, we have ice bands at 7, 10, and 12. And you can see that 7 bands is definitely a little bit, not as good as I want. So here I can see that I have an area, this green area, I have orientation space that I definitely have problems getting unique orientations. And really I kind of want this to be mainly orange or red, and I can see some yellow areas. So I have areas here that I want better CIs at. So if I use 10 bands, I can see, hey, I'm doing a pretty good job with some of this being yellow, again, a lot of it, being red and orange. And if I use 12 bands, I can see the average CI now is a little bit higher, but of course there are certain orientations that, again, are a little worse than perfect, but again, it is what it is. So again, 7 bands has some areas, like here in green, that I would not get a perfect orientation off of. As I use more bands, I have more. And if I go ahead and do this now with ice, again, here you can see, in this case here, I'm still getting some of that speckling. I want to go ahead and deal with this. So I go ahead and use more lines. I can see that I get 10 bands. I've now basically got rid of that speckling problem. The grains are no longer speckled inside because, again, I have enough bands to do that. Again, here you can see I'm getting some grain boundary speckling, but that's just kind of the nature of the sample because it's getting low Z. The patterns are highly convoluted, and I'm just not really going to be able to kind of pull those all the way out. But even though with 12 bands, again, you see it gets a little bit better. There's less internal speckling. Grain boundaries are slightly better. But again, it is what it is. So again, is the difference between 10 bands and 12 bands worth it? Maybe. I don't know. again, depends on what your kind of your end goal here is for your data itself. With that, I am going to kind of leave one kind of final question for you guys. So this is what I would call the basics of the basics, kind of talking about the minor parameters that I can change to kind of change what's going on with the indexing routine. Again, understanding a little bit more about the indexing routine. Now, of course, with that in mind, I really wanted to kind of know, what do you guys want? What other topics would you find interesting for this? And that would be like deeper into the basics. You want more knowledge of things behind the scenes. And I'll tell you, some of that wouldn't be me. Some of that I definitely would toss over to Stu and say, hey, you're the one who actually wrote the code. You say why you did it. Of course, more data set troubleshooting. I want to see, kind of how you kind of work through common problems and apply them to mine. So again, I got this customer data set from a customer, and I was able to kind of step by step through this, say, hey, here's how I would do, things that with your data and do that. Of course, that means I'll need your data to do so. And of course, more general how-to topics. I try to focus most of my webinars on kind of step-by-step guides on common procedures and how to do that. So kind of interested in see what the results are going to be with this. Cool, nice even split here. So nothing really kind of stands out to you. So some of you guys want deeper into the basics and I want more knowledge. And again, I tell you that some of our webinars already cover that. So always can go back to EDAX webinar webpage, and I think there's 5 years of current webinars up there. More data set troubleshooting. Again, want to work through common problems and apply them to mine. Again, I'm happy to do that. I just need your data sets and don't all give them to me in the next day and a half because that won't help. And then of course, general more how-tos. So again, you guys were pretty kind of split on that. Now, with that in mind, at this point, I would ask you for questions. So this would be your final chance to ask questions. I got a couple over here to discuss, but honestly, you guys have been much quieter than what I thought, and I'm not sure that's a good thing or a bad thing. So hopefully, again, you guys gathered some good information out of this, and I can take a use that. So again, final chance to ask me questions. Of course, you can contact me at there's my email address, and of course, I will be at both EBSD 2020 at the University of Michigan, and of course, M&M 2020 in Milwaukee. And of course, again, a thank you to my colleagues here at EDAX, Matt, Renee, and Stu for some of the data and the content, and of course, our good old friends over there at the University of Pennsylvania, and Dave Pryor for, of course, sharing the data set. So I get more resources, and while you guys are looking at those, I will go ahead and answer some of the questions I have. Will vertical bias change is needed for BCC or FCC? In general, no. A BCC or FCC default settings work for darn near anything, unless you start to get a little bit. Some phases of steels can definitely have problems, but in general, generic FCC, BCC, and default settings work for steels, for base steels. With that, somebody asking about why does the outside of the 6 bands, I believe he's talking about my dual phase titanium. Why does the outside in 6 bands show up yellow? When we go up to 10 bands, we see the outside orientation can go a little bit green. Good question. So here he's saying 6 bands versus 7 bands. You can see on the outside here that they go a little bit green and they get a little bit worse. And honestly, I can't answer off the top of my head. I have to think about it a little bit more deeper than 2 minutes here. But yeah, you can see that 6 bands gives you better orientation and precision around the outside versus, of course, the middle here is not great. And then if it actually gets kind of goes back and forth. It gets worse, it gets a little bit better, it gets worse, and then it gets better. I honestly don't know the specifics as to why. Okay, somebody asking a question about, yep, this is one of those good questions. How do I know which reflector to activate? I frequently have the problem in the CI simulation of material files in Hough settings, etc. They look fine, but the scan still looks horrible. So the easiest way to do that is what's going to be called band detective. There's a, do I have that on my slide or not? Give me a second here. Again, it's a really good question of how to do, reflector characterization or optimization, which is something I didn't really cover in this guy. Let's see if I can find what I'm looking for in my currently existing slides. It has to be here somewhere. So there's this thing called band detective that kind of can help you do this. So if I look over here on this left-hand box here, there's this guide right above where it says reindexing on the left-hand side. There's this line with a question mark. And what that does is it essentially says, okay, here's my Hough lines. If I index this, I can see maybe it didn't index one of these lines. What I can do is I can click on this band detective button and then draw a line over it, and it's going to say, hey, you just identified the, let's say, the 111 band. Do you want to activate this reflector? And you can click on yes. Now, if you go ahead and draw that line, it says, hey, you just drew a line on the 11919. Don't activate that one. Again, the symmetry could kind of make sense. Go ahead and redraw it and redraw it. So you can basically say, okay, hey, if this is the line you found, I can essentially add that to the reflector list using this band detective, and that's kind of how I would do that. Again, really kind of a good question. And again, I think it's kind of a known problem with some micas is that they, again, what bands you get, I think is controlled a lot by what element you have where in the crystal structure, because again, that kind of controls the actual what reflectors we see. Quick question. So somebody's asking about the parameter of fit and how fit talks about the reliability of the indexing in general. Fit is a parameter that essentially says, here's what the Hough found, here's what the orientation solution found. What is the difference between these two on average? And fit is one of my main kind of parameters I do use quite a bit. But you have to think about why there is a mismatch between the fit and what I have. So let's see, we're doing on time. Okay, we're okay on time. So with fit, I need to think about, again, why do I have this difference between what my Hough found and what my indexing solution found? And the easiest thing to think about here is if I had deformed material, I no longer have a perfect crystalline. I no longer have that perfect unit cell. It's been distorted. So what my Hough is what my lookup table and orientation is trying to compare it to is different than what my sample is because it's deformed. So I'm going to kind of have this fit be different. And honestly, fit values, they should be in the 1.5 range for most materials, 1.5 degrees. If I start getting over to close to 2, I really need to think about why it's wrong. And in that case there, it's usually either the phase file is wrong, or again, maybe my sample's heavily deformed, or of course my calibration could be wrong. So if everything is kind of off and my fits are bad, often it can be a calibration problem. That's something to look at, but that's usually pretty easy to fix. Let's see here. Let's see. Somebody asked how to index multi-phase steel microstructures in the martensite and ferrite. I believe there's actually an application note on that, and I'll go ahead and try to send that note to you. Again, it's usually, it depends exactly what level you're looking at, but it can be done using things like IQ as a kind of a differentiator. And yeah, so another question about the mica. There are no acceptable bands in the location of the Coochie lines. They're just the wrong SIF file. Yes, it really could be just the wrong one. Again, with a mica kind of being generic, it'll have either the wrong spacing or the wrong atoms in the wrong position, so you'll get different strengths of different lines. So yes, it can actually be a different SIF file, or in this case, what we could use we call ours BMTs by default. Yeah, I would start trying different micas in whatever database you can find. Again, go to the AMCS, the American Mineralogical Crystal Structure Database. Will have a whole bunch of different micas, and just kind of start, kind of going in there and saying, hey, what can we do, and go from there. And then with that in mind, I have a couple other questions, and I'll go ahead and answer those offline, I do believe. But some final housekeeping. Of course, we do need to talk about our upcoming webinar. Dr. Stuart Wright, our senior scientist for EBSD here, will be covering EBSD analysis of deformed microstructures. So we'll be talking about the, how these different kind of deformation maps do, how they kind of tell you different things about your sample, and of course in the end what you can do if you want it or don't want it, kind of thing. So again, another good webinar, and of course next month, late in the month, we always try to do these around the third week of the month. So with that, I'm kind of done, guys, and thank you. Very good attendance and good questions. If I didn't get to your question, I will try to, of course, answer them offline via email. So again, thank you guys for joining me, and I hope you've found this useful.